everybody. Welcome to this session where we're going to see the details behind this new concept of AI at scale. So this generation of AI that is powered by massive AI models trained on these huge AI supercomputers. And we're going to see the technologies and also a little bit the breakthroughs, the research breakthroughs behind all of these innovations that are enabling this new breed of AI. I'm using for this like a little experiment in here, so you can see that behind me I have like a virtual whiteboard, and I can actually draw in that whiteboard as I speak. So wish me luck because I'm a terrible drawer, but I will give it a try. Okay, so what is going on with these massive models in the last couple of years? So if you look at them in a timeline, you're going to see that, imagine that this is the size of the model and this is the time. In the last couple of years, and in particular for NLP models, so for natural language processing models, we are seeing a huge increase in the size. So we started in 2018 with GPT, a model created by OpenAI, and it had 110 million parameters. Then we saw BERT coming from Google with 340 million parameters. Then after that, GPT-2, 1.5 billion parameters, and at the beginning of this year, you probably remember, we announced in Microsoft Turing, the family of models Turing, with 17 billion parameters. After that, using the same infrastructure in Azure, this AI supercomputer in Azure, OpenAI announced just before summer the GPT-3 model, and this one had, wait for it, 175 billion parameters. So you can see what is going on here. So there's like this huge like exponential growth, right? Well, GPT-3 is not even in the chart anymore, right? It's above the chart. So we're seeing this huge growth in the size of the model. But what is even more important is that there's also an increase of the quality in the model, and even we are learning as we add more and more parameters that the models can perform tasks that they couldn't perform before. So we haven't reached the ceiling here. We expect for the next months and even years continuing growth in that size of the model. So why is this happening now? Why didn't we add more parameters before? The answer has to do with the research that was done to enable these new massive models, right? And for that, to explain those breakthroughs, I need to explain a little bit how NLP works. And this is interesting because I will refer to this as traditional NLP, but this technique in particular started like in 2013 with a famous paper. It's called word embeddings. You're probably familiar with it. And word embedding, so the way that that technique worked is that you could map words to vectors, and usually those vectors will be huge vectors like 300 dimensions, right? But let's imagine that is only 2 dimensions. So a word embedding will take every word and it will map it to a vector here. Now the interesting thing is that at the end you're going to notice patterns like this. So you will have words that are closer in meaning to be closer as vectors. So king, queen, prince will be closer between them than red, blue, orange. And this is a very simple example with 2 dimensions, but this could be very, very complex in multiple dimensions. So what is behind this is a mathematical representation of the word that has to do with the meaning of the word. So that's very powerful because now a computer can use these word embeddings to do something with them, representing their meaning. So the way that we calculate these word embeddings is it's like an approximation. So we're gonna estimate that the meaning of a word has to do with the words that are usually used around them, right? So if you do that with a lot of text, for example, the entire text coming from the internet, the result of that is actually very good, and it has a lot to do, that representation, with their meaning. So now that we have this mathematical representation, we can do things like a language model. So a language model is very simple. It's a foundational, we call it a secondary task in NLP because it's very basic. A language model will take a sentence. Imagine that I have the sentence, I am loving Ignite. And the model will try to guess what is the next sentence, the next word after this. So to do that, I can do something very simple. So I can take a word, for example, let's take I can calculate that word embedding, so I can get the word embedding, the mathematical representation, and then I will use that as an input to a neural network that will provide as an output what the model thinks will be the next word after I. And I can train this neural network with, again, a lot of text coming from the internet, right? With a lot of sentences with the word I on it. And this is great, but it has a problem. It only takes like one word as an input. So usually you're going to need to consider more than just the last word to guess what is the next one. So what we do is a technique called recurrent neural network, or RNN, where kind of the neural network has memory, right? Because it gets as an input not only the word, the input, but also itself. So it is connected with itself. And there are many types. I won't get into that detail, but they all look very similar. So if you unfold them, you're going to see that they all take like a shape like this. So it will take the first word, and then it will take the second one in the next iteration of the neural network, taking not only that input, that word as an input, but also the internal state, right? So that hidden internal state of the neural network. Then another iteration with the same neural network taking as an input that new hidden state and the new word, and it will take an output. And then in the last one, again, same thing, the hidden state and the last output. If I train this neural net, it will give me then an estimate of what is the next word, for example, because. So that is a basic language model. Now the interesting part in here is not actually this because, forget about this. The interesting part here is this age. Because if you think about it, age is like the state of the sentence, right? It's a representation of that sentence. So in a sense, it's kind of the meaning of the sentence before this particular word. So at the end of this last hidden state, that is going to be another vector representation of the meaning, but now not for a word, but for a sentence. And I can do crazy things here. So for example, imagine that I have now a labeled set of sentences. I can classify them whether they are positive sentiment or negative sentiment, right? So I can create groups, like manually labeling those groups with positive sentences. And imagine here I have like negative sentences, like I hate Ignite. Now, when I train that model, what I have is a classifier, so I can take now a new representation of another sentence. I can run it through this model, and the output, in this case, I am loving Ignite, is positive. So I created my first like sentiment analyzer, right, by using this concept of recurrent neural networks and word embeddings. Perfect. What is the problem of this approach? The problem of this approach is that it doesn't scale. So every step relies on the previous one. So I need to execute all of this sequentially. And that is blocking us for adding more and more parameters to it because we can't scale. Now the trick here, so the breakthrough that happened in the last 2 years is a series of, like, think of it like neural network techniques that are allowing us to increase the size of the model without impacting on the scalability of that model. So the main concept is called transformers. So that's the primary architecture concept for this. So the main trick in here is thinking, okay, I have the same sentence. I am loving Ignite. But now, instead of connecting this to a recurrent neural network, I'm going to connect every word with a traditional feed-forward neural network. So it's not connected to itself, so it can scale. Now, this is not going to work, right? It's not going to work because of several reasons. So the first one is that if you see here, the sentence just lost the order, right? So every neuron wouldn't know what order every word is. And that is important in a sentence. So it's not a collection of unordered words. So to fix that, what we're going to do is that in the representation of every word, we're going to add information about its position. So that was an easy one. I can easily fix that, right? And this could be 1, 2, 3, 4, depending on the position. Usually it's a little bit more complex, like a sine or a cosine, but that's the idea. So that's the first thing. The second thing here is that if you look at this, every neuron doesn't know more than one particular word. So the representation of it would be very tricky. I need to understand what is the context for every word. So for example, imagine that I add here not. This not is changing dramatically the meaning of the word loving. So when I'm processing loving, I need to be connected. I need to get that context to understand that in this case, it's not a positive thing, right? So not loving is very different than loving. So to fix that, we introduce another very important concept that is called attention. And attention, the attention technique is being used in neural networks for very long, but not in this particular concept of transformer. So how does it work? So let me just remove all of this here very quickly, because the way that this works is very similar. So what I'm going to have in here, imagine that I'm going to have a similar sentence, but in this case it's going to be, I don't love Ignite. But now this sentence, instead of just feeding directly the neural networks that I have in here, I'm going to add a new block. I'm going to call that block, this is going to be called an attention block. An attention block is going to do the following. Instead of just taking these words directly and passing them through the neural network on top of me, instead of doing that, it's going to pay attention to other words that are associated with this one. For example, in this case, it will, because of training, it will understand that don't is connected to this one. And then it's going to mix these two. And usually this is as simple as just doing a weighted addition, right? So you just take like an average weighted addition, right? So you just take these words and you mix them together, and then you get the output of that representation and you pass it to the neural network on top of you. It's that simple. Then it can get more complicated because it's usually more than one word, right? So words are connecting between them in multiple ways. And it could be, there could be a lot of distance between those words. So in this case, imagine, for example, Ignite. Ignite could be catching fire, or it could be the Ignite event. And to know that, I may need to go like 3 sentences before to understand that, hey, I was going to this Microsoft event. So all of these, those 2 tricks, that is the transformer architecture. And once you have that, here's the magic. You can scale it any way you want, because now you can say, okay, let me add, for example, like multiple layers here of attention blocks. Or I can increase the complexity of this neural network here. Or I can add something that is very common in this model, which are attention heads. So I add multiple attention heads. They are called multi-head attention blocks. And each block, each head will look at particular relationships between words. So each one will be specialized on a particular association between words, and then the addition of them will be combined, and that will be the output of this attention block. And this is all trained. All those weights, all those parameters are learned by the model itself when we train them. So then this whole thing, which is called a transformer block, I can add multiple layers in here. So I can scale that even more by adding multiple transformers, one on top of the other. So for you to get an idea, in the case of, for example, Turing, one of the variations of Turing that we announced at the beginning this year, that one has 28 attention heads, and it has like 78 layers of transformers, right? So you can see how this can grow a lot. So let's talk more about this Turing model. So let's see how all of this now relates to the Turing model that we talk. And for that, I have invited Ali Alvi. Ali works in the team that is behind this Turing model, and he will show us a little bit more in detail. And even I think, Ali, you have some demos to show us. So all yours.
Thanks, David. Great to be with you today. Hi, everyone. My name is Ali Alvi, and I'm the GPM for Turing team here at Microsoft. I'm very excited to talk to you about Microsoft Turing models and their capabilities and how they are fundamentally transforming the way we think about using AI models in production here at Microsoft. I will show you a demo of how easy it is to use these language models for any NLP task. And at the end, I will talk about how cutting-edge platform innovations and Microsoft Azure AI supercomputer make it possible to train these large-scale models. But let me start off by explaining the different types of Turing models and their capabilities. I will be using this whiteboard as we go along, so I apologize if things are not very legible, but we can always blame David for putting me up for this. So let's, first of all, look at what are the core NLP capabilities of Turing language models. So in any kind of an NLP task, you always start off with text. So here we have some text. It's called I love AI. And we're going to pass this text through our neural network model. And this network is going to think about this text, process this text, and it's going to create what we call a representation of that text. And it's basically a mathematical representation of that piece of text. Now, a model that does something like this is called a representation model. And Turing has a Turing natural language representation model. Now, that's just one type of model. Now, you can imagine, let me change colors and also change the input to I love neural. Now, this is a different kind of an input, and this goes through the same model and comes up and has a different representation. Now, there are models that can take that representation and have a different component of these models that does some processing, and this time I'm going to have a different kind of an icon because this model is kind of thinking about this. And this model then outputs not a representation, but actually networks, which is a piece of text. So this is a different kind of model because this model takes in text and produces new text. A model that can do something like this is known as a generation model. And Turing at Build announced Microsoft Turing NLG, which is a generational model. It's a 17 billion parameter model, which was the biggest model at the time. That is a generation model, takes in a text and produces new kind of text. Now, both these representation and generation model example that I showed you are performing, working on English data. However, you can imagine, that this input could be any different language. So let's assume, change colors again. This input could be English, could be Cyrillic, could be Chinese, Japanese, and model that takes in such kind of an input and creates a representation. Now this is going to be a different representation, and this is a universal representation. Such a model is known as a universal representation model, which basically means that this model is language agnostic. It can understand many different languages. And Turing has universal representation models as well. Now you can take the same analogy forward, and a model that can actually take this input and output all different kinds of languages would then become a universal generation model. And that's another kind of capability. So essentially, when you think about it, there are two dimensions. One is the type of capability, which is representation or generation. And then the other aspect is whether the model is monolingual or universal. And as part of Microsoft Turing family of models, we have models that represent all of these NLP capabilities. And these are fundamental capabilities that are required to perform these natural language tasks that we see all over Microsoft. Now with that, I'm going to quickly transition over to a demo, which is going to show how easy it is using Azure Machine Learning to use one of these language models. It's going to be a language representation model in English, and fine-tune that for a sentiment analysis task with just a few lines of code. So let's transition over to the demo. This is the Stanford Sentiment Pre-Bank task, which is part of the GLUE benchmark. I want to highlight that when this task was published just over a year ago, the baselines for the task were bidirectional LSTM models with some attention mechanism that could get you accuracy of around 85% on this task, which was considered significant at that time. Let's see if we can beat that baseline using a powerful language model like Turing NLR. I will be showing you how to do this all inside of Microsoft Azure Machine Learning. Here I am in my AML portal, and I have set up a Python notebook running inside of an Azure ML Notebook VM, which gives me all the configurations necessary to get started with this task. I will first show you how to fine-tune the model, and then also show you how easily you can convert the model using Onyx Runtime and then deploy it as a service on a CPU, all this in a handful of steps. Let's get started. First off, we simply initialize the AML SDK and create a workspace using my subscription and configuration. Next, I'm going to create my compute cluster. This is the GPU cluster that we will be using to train. The one I have chosen is a single node with 4K 80 GPUs, since this is a simple fine-tuning task. I'm also registering my data store where I have already placed my pre-trained TNLR model. This is the same data store where I will upload the GLUE SSC task to. Last thing in the setup is to create a custom environment based on an existing Docker image that has all the dependencies I need for the NLR model. Now we have everything ready to go. We copy the code to the GPU and then run the fine-tune script. The key settings to note are that we are using all 4 GPUs and training this with a batch size of 32 per GPU. We will run this for 15 epochs. I can now submit the experiment. Once submitted, I can easily go over to the Experiments tab and see that my experiment was just queued and is starting. It will take a couple of hours for all 15 epochs to run, but I have previously finished a run and I can show you that using Turing NLR v3 I was able to get an accuracy of 94.5 on this task in 15 epochs. In fact, you can see that after just 2 epochs, the model was able to go well beyond 92% on this task, which is significantly better than the baselines I shared before. The rest of this notebook talks about how you can optimize the model using Onyx runtime and then use AML to deploy this to a CPU inference cluster. In the interest of time, I'm not going to go into all the details. However, I have the model deployed to show you how this model does on some interesting examples. The first example is a simple example of someone saying the movie was worth 2 hours of my life. This example is classified correctly as a positive example. Keep in mind, 1 is positive and 0 is negative. The next example is a bit tricky because it uses some of the same words as the first example, where the user says, I would really love to have 2 hours of my life back. Notice that even though the word back is misspelled and the review has the words love and life, the model correctly predicts this as a negative review. Next one is an unusual review that you would normally not see, but the model also gets this one correct. Next example has a phrase like, if the kids are bored, but the model is able to tell this is still a positive review. The last two are interesting as the term horror appears in both of them, but the model is able to tell that in one case, it is talking about the movie genre and has positive sentiment, but in the second one, it is talking about the movie being really bad. This concludes the demo of how using powerful large-scale language models like Turing NLR, you can get state-of-the-art performance on some real-world natural language tasks. Now let's quickly take a look at how the same Turing model is powering Smart Find functionality in Word. I have Microsoft Word open with the document I am viewing. I can press Ctrl F to get into Smart Find and simply type what I'm looking for. I made a mistake in spelling exposure, but the Turing-powered Smart Find automatically corrects it and finds me all the places where those words appear in a phrase. I could completely misspell something. As you can see, I have no clue how to spell that word, but I'm still able to find it in the document. Turing models can even make things like question answering possible as shown here. The Smart Find model extracts the answer to my question and points me to the exact part of the document that contains that answer. All this is made possible by leveraging the power of large-scale Turing natural language representation. As David mentioned, we have AI models that are billions of parameters in size. The GPT-3 model from OpenAI is 175 billion parameters. And I fully expect that these models will grow to over 1 trillion parameters in the next year or two. Personally, I'm super excited about that, but it does make you wonder, how do we train these AI models? This is a remarkable accomplishment on AI platform engineering. And this is another area where Microsoft is at the cutting edge of innovation. So let me quickly try to explain to you, how do we train these large models? There are fundamentally 3 things that you need in order to train an AI model. The first thing is you need to have data. The second thing is you need to have your model. And the third thing, which is the most important innovation of all of this, and without which we could not be able to train any of these models, are GPUs. So you need to have a GPU resource. So let me draw a GPU. This is my GPU. Now, traditionally, what you do is you put the model on the GPU, and then you take this data and you pass all of that data through that GPU, and that's how the model learns. Now, that is what would traditionally be known as a single box learning, and it works fairly well for a large number of neural networks. However, in order to train a language model, we need to have a lot of data. And when you have a lot of data, doing something like this is going to be very slow. So what we need is more compute. So let me quickly try and expand my GPU hypercluster. Add a couple of more GPUs to this. Now I have multiple GPUs. What I can do is, when you have more than one GPU, you can take this data and you can slice it up. Let me change colors. So you can take one slice, put it on one GPU, take another slice, put it on another GPU, and take another third slice. And this, if you have 3 GPUs, put the third slice on these GPUs. Now these GPUs need to be interconnected at very high speed connectivity. I'm talking about hundreds of gigabits per second, because in order for the model to learn from all of this data, these GPUs need to be connecting and communicating all the time. I'm not going to go into the details of those, but that's just an important fact to remember. Now, what we've essentially done is we've split up the data into multiple shards, and we've put the same model on all of these GPUs, and now that model can learn from all of this data. This kind of a division or parallelism is known as data parallelism. So you take data and then you parallelize it across multiple GPUs. Now this opens up a lot of opportunity. Now you can have a lot of data, and then all you really need with the ability like this is to add more GPUs, and you will be able to train more data, or train with more data. However, there is a problem. The same model exists on all of these GPUs. And these GPUs have 16, maybe 32, 64 gigabits of memory. We're talking about models that are billions, hundreds of billions of parameters. So after a while, when the model becomes large enough, your GPU is going to run out of memory. So how do we solve that problem? So let me just quickly expand my GPU hypercluster. I'm going to add maybe 3 more. Let's just go with, another 3. So let me quickly grow my GPU hypercluster to 9 GPUs now. And now what we just did with data, we can kind of start to do with the model as well. So let me see, you take this one part of the GPU, put it on of the model and put it on this GPU. Take another part of the model, put it on this GPU, and then take the third part of the model and put it on that GPU. So by doing this, now you've done exactly what you did with data, but with the model. So now you can imagine this model can continue to grow, and all you really need is to add more GPUs in this second dimension. And this kind of way of increasing the capability of the size of the model that you can train is known as model parallelism. And coupled with data parallelism and model parallelism, now you can imagine all you have to do is just keep increasing, depending on whether you have more data or you want to increase the size of the model, just increase the GPU hypercluster in that dimension, and you will be able to train very large model. However, can we do more? So as David mentioned, these models are built of layers and layers of transformers. So if you think about it, when we have 12, 24, 36, 48 layers of transformer, they're just identical transformers built stacked on top of each other. So essentially this model is kind of like a pipeline of transformers. So if I extend the same analogy across the model as well as with my GPU hypercluster and extend it into this third dimension, and let me draw another GPU here, and then imagine you have GPUs in this direction and the other direction also. Now I can take this model and exactly do what I did explain to you in terms of data and model parallelism, and I can do that with this model over with this GPU or this set of GPUs. And now I can actually parallelize the model itself in terms of its layer across many different GPUs. Now this kind of a dimension of parallelism is known as pipeline parallelism. Now together with data parallelism, pipeline parallelism, and model parallelism, you can imagine now all of a sudden models that would take months or years to train can now be trained in a matter of weeks or sometimes days. Microsoft provides all of this support as part of our DeepSpeed with Zero library. This is available on Azure, and all you really need to do is add this library into your code, and you will be able to get data parallelism, model parallelism, and pipeline parallelism all at the same time. And we call this thing 3D parallelism. Now this is a fantastic library available for anyone in the world to use. And by doing this, you go from training models that are less than, maybe a couple of 100 million parameters to 10 billions of parameters, and then using the model parallelism and pipeline parallelism added on top, you can go up to like hundreds of billions, even a trillion parameter model. Now, of course, we need a lot of GPUs, and we have something which actually has more than 10,000 GPUs and even more than 285,000 CPUs, and this is what we call the Azure AI supercomputer. This is what OpenAI used to train their 175 billion parameter model, and this is also the same supercomputer that Turing uses to train all of their models. So you can see Microsoft with DeepSpeed library is providing the software support to be able to expand and extend the training of these large-scale models, and also we are providing the supercomputer to be able to train these models.
Thank you, Ali. So I hope you enjoyed this presentation about AI at scale. If you want to learn more about it, I encourage you to go to this URL right here, aka.ms/AI at scale. And in here, you're going to find a lot of information about the technologies, the research, and even examples and access to the latest technologies that are making possible this like new generation of AI. So you can also reach out to me for any question at David CSA. This is my Twitter, LinkedIn, or email elias@Microsoft. You have any question for Ali? Send them to me, and I will also chase him for any answer. Thank you very much. Bye.